khususnya saat ini tentang fundamental concept of VO2max. Oke, pada kesempatan kali ini, monggo persilahkan Bu Profesor Tanja Rahayu untuk memberikan welcome speech ke Profesor Fabian Lim. Waktu dipersilahkan.
Baik, terima kasih Mbak. Bisa dengar suara saya ya? Sudah ya. Baik, terima kasih Bu Sri Sumartiningsih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon and best wishes to you all. I hope everyone is happy and healthy. Our distinguished guest, Professor Fabian Lim, Professor, on the behalf of my faculty and of course from the Department of Sport Science, I would like to deliver our appreciation. Thank you very much for your willingness to take your valuable time to share knowledge and of course broaden the horizon of UNES students.
Thank you.
And to all students here, thank you so much. Today you are all very lucky because you will get lots of knowledge from the expert, and therefore please follow this lecture orderly and carefully in order to get lots of benefit of it. Professor, once again, thank you very much. And I would like to thank to all participants here. I heard that there is also Professor Raymond Ong. Prof. Raymond, are you here? Mr. Raymond? Hi.
Hi.
Long time no see.
Yeah, nice to see you again.
Nice to see you.
Yeah.
Okay.
To hear that you are organizing this webinar.
Yeah.
Dr. Fabian Lim is the guest speaker.
Yeah.
Hi, Fabian. This is Raymond here.
Hi, Raymond. Very nice to see you.
Oh, hi.
Yeah.
Okay.
Glad to hear that you are delivering your talk on this webinar.
Yep.
Yeah.
Thank you. Thank you. I'll try my best to make it worth it for everyone.
Okay. Prof. Fabian, thank you very much for your precious time.
My pleasure.
Thank you. And the screen will be back to Miss Sri Sumartiningsih. Please.
Thank you very much, Professor Tanja Rahayu, for your welcoming speech. And Alhamdulillah, today we will have a good chance to study about exercise physiology from the expert. That is Professor Fabian Lim from School of Medicine, National Technological Nanyang University, Singapore, and he is the expert in exercise physiology in there, and also she's a member, the professional member in Federation of Asian and Oceania Physiological Society. He is the Executive Director, Singapore Sport Institute Council from 1st June 2011 until 17 March 2014. And now, present, he is a Program Director for Graduate Diploma in Sport Medicine in Lee Kong Chiang School of Medicine, Nanyang Technological University of Singapore. Please welcome Professor Fabian Lim. Now, The time is yours.
Thank you. Thank you, Professor Rahayu. Thank you, Professor Tintin, for this opportunity to be here. It's indeed a pleasure. And I trust that everyone is well. Despite COVID-19, I'm glad that we're able to find ways to meet and to share knowledge. This is the wonder of technology. And I trust that everyone is well. I'm not really an expert in exercise physiology. I just have the chance to be able to do more work in this area. I spent the first 20 years of my career doing exercise, using exercise physiology to do research on soldiers. Yeah, and then subsequently I was able to use the same knowledge to apply that into elite athletes in Singapore. There's in Team Singapore athletes. And then in the last few years, I've been able to have the chance to do that also in older people, looking at how exercise can help in aging health. And in the midst of all this, you find that exercise science actually is a very, very useful set of knowledge that you gain because it's very integrative. It looks at the human as a whole. It doesn't just look at humans, it looks at how the human interacts with the environment. It looks at humans over lifespan, and therefore it's something that is very useful and to society and as well to the individual. So what I hope to share with you this afternoon is the fundamental concepts of VO2max. When Professor asked me to give a lecture for today's session, I thought that since this is our first time, VO2max would be a good topic for sports science, because if you're in sports science, you know, from the day you start studying sports science to the day you retire, you will always come across this term called VO2max. VO2max can be something that's very simple to use, simple to apply, but actually there's a lot of science behind it. And understanding some of these fundamental concepts can be very helpful in allowing us, each of us, to use the concept, to apply it in the places where we work in, the people that we teach, so that, you know, it becomes something, can be something that enhances our practice in sports science. So without much delay, I'll just go to my set of slides. Is it okay I share my slide, Tintin? Yeah, thank you. Yeah, sorry, just before that, so the plan for today is this: we have 2 hours, and I'm going to try to do the first part in 15 minutes, and then we will have a.
Mr. Fabian,
yep.
Sorry for interrupting. But please, can you share your presentation over here?
Sorry, I can't hear you.
Can you share your presentation over here?
Yeah.
Because we are not seeing your presentation on here.
Yes, I will be putting up on the screen.
Okay.
A copy, is that what you're asking for? A PDF copy?
No, but please
on the screen?
Share your screen.
Yeah, I will. Give me a minute. I haven't shared screen yet.
Okay.
Okay, just give me a minute. So I just want to let everyone know the plan for today. I will speak on the background and science of VO2max in the first part. That will be about 15 minutes. And then we will take 10 minutes to take question and answer. Because this is a long lecture. If we wait to the end, you may not remember your question for the first part. So after the first 15 minutes, we'll take 5 to 10 minutes for Q&A, and then we'll continue for another 15 minutes on the application of VO2max in the different scenarios, and I will show you some research evidence as well. And then that's another 15 minutes, and then towards the end, we'll have another 10 minutes of Q&A. So I see that there are about close to 200 participants. I hope that you have enough questions to fill the 5 to 10 minutes. Okay, so here we go. Let me share screen now. Yep. Are you able to see my screen? Good. Yep.
Yes, thank you.
That's great. Yep. Okay, it's coming along. All right. So this is the topic for today. And as I said, VO2max is something that people who are practicing sports science uses a lot. whether is it in practice or is it in research. So if you read research paper, you find that it appears in many papers. And sometimes they use different terminologies. Sometimes they use VO2max to measure different form of work. But they all come down to a similar set of fundamental concepts that I'd like to share with you in the next 2 hours or so. So I want to start by going back to history. I think it's important to know where it starts from, and because that's how the concepts gets generated. The idea of VO2max was developed sometime in about 1923 to 1925 by this physiologist known as A.V. Hill. A.V. Hill, before this in 1922, he actually got the Nobel Prize for physiology and medicine for his work on muscle metabolism. And because he works on muscles and heat production in muscles, he was interested to see how the same physiological functions can apply to physical performance, to human functions on the move, right? In sports and in work. And his concept, when he first came about with the concept of VO2max, his idea was this, that the physiology demonstrated that oxygen uptake will increase linearly with speed. Yep. And at some point, eventually, oxygen will reach a maximum beyond which there will be no more effort that can increase. Yeah. Okay, thanks. Okay, so that's the key concept of VO2max. Now, this concept about the linear relationship between oxygen and work, running speed is work, right? As speed increases, oxygen uptake increases. And the second idea here is that at some point, you reach a point where no matter how much more you try harder physically, there will not be any more increase in oxygen uptake anymore. And that's the point we define as VO2max. So this was the concept that was brought about in 1923, 1925, and it is still the same concept that we work with today. So when we deal with VO2max, understand that we're looking for the plateau, the workload where the oxygen uptake plateaus off, where there's a dissociation between workload and oxygen uptake. No matter how hard more you try, oxygen uptake doesn't increase further. And so with that concept, VO2max physiologists around the world started measuring VO2max, and the earlier ones looks like this, very rudimentary. So as a person walks on a treadmill, his expired air is then piped into two different sensors. Yeah, one is for oxygen and one is for carbon dioxide. There's another sensor for air volume. And although what you see on the picture looks very backwards, looks very old, in today's machine, the same principle still applies. Okay, it's just that today the machines are a lot more modern and with more modern technology. The picture that you see on the top left, this was one of the very early attempts to measure VO2max in the field. With one person cycling with a few Douglas bags, and then the subject is running by the side where the expired air is collected in the Douglas bag. So Douglas bag is one of the earlier form of collecting air for measurement of VO2. So as you run, air is collected in those bags, and then those bags are then brought back to the laboratory and they are emptied into sensors for oxygen and carbon dioxide. And from there, we determine how much of O2 and CO2 is being expired during the physical work. One of the early set of data that A.V. Hill produced in 1925 was what you see on the screen here. This is not data that was collected on human subjects. He basically, because those were not available at that time, he basically went to get a book that was published that had the world record of men and women swimmers and runners at various distances. So if you see my cursor on the x-axis over here, this will be time of exercise, the duration of exercise, right? In hundreds of a second. So the fastest would be 1,600 seconds. That's about 20 over minutes, right? And then on the y-axis over here, that will be the speed, whether running speed or or swimming speed. Yep, and for men, you can see that they went quite long for running and swimming. For women, the distances, the duration went quite long for swimming, but for running, you notice that you only went for about 200 seconds. That's slightly more than 2 minutes. And that was because up to that point, even at, this was in 1920 something, women were not supposed to run more than 800 meters. Yeah, that was the thinking then, that beyond that, it would be not good for their health. And that's why in the Olympics, women event beyond 800 meters was not included until after the if I'm not wrong, 1968 Olympics, 64, 68 Olympics. Yep. And but I'm trying to explain to you why the women run shorter distance over here. But the main point over here is just by plotting work duration on the y-axis and then speed on the y-axis, this is in yards per second, how many yards you can run per second. You can see that there is a negative relationship between work intensity and time, right? So as speed goes up, the duration of work gets shorter. So, right? So in order for duration to last longer, like in these events over here, the speed would need to be within about 1.2 yards to about 5 yards per second. That's the kind of speed that can be sustained. Above 1.5 yards per second, you find that the exercise duration gets shorter and shorter. Yeah, every dot here is the finishing time for an event. Yeah, how long the person took to finish that world record at a particular speed. So this was calculated. He then took the same set of data and he plotted in another way. He tried to estimate what is the oxygen uptake if that was the running speed. So he had running speed on the x-axis over here, right? So the more you go to the right, the faster you're running. And then on the left, he estimated oxygen that would be used in running that distance or swimming that distance, okay? And from here, he was able to plot the positive relationship between running speed and oxygen uptake. Yeah, it was a very simple study, and it was calculated. Those data were calculated and were not collected. But it developed a very important concept in the way humans utilizes oxygen in relation to work intensity. So that was the foundation for VO2max. These were the data that started people thinking about the relationship between physical work done and oxygen uptake, and the question of whether could oxygen uptake be a limitation on physical work done, all right? And that generated research in the last 100 years or so, yeah? So you fast forward today, yep. The idea of measuring VO2 or VO2max has gone beyond sports and occupation, and it's really now populated extended to the public health, chronic disease, even in aging health. Yeah. So, for example, in public health study, where we're looking at the health of the population as a whole, there's a very well-established relationship between poor VO2max and all-cause mortality, meaning that the poorer VO2max one has, the higher chance of dying earlier, the higher is the chance of dying earlier at the population level, okay? Secondly, also CVD refers to cardiovascular mortality, meaning the chances of dying from cardiovascular disease. And again, there's a very strong negative relationship with VO2max, meaning that the lower the VO2max, the higher is the chance of someone to die from cardiovascular disease. So between VO2max and mortality, lifespan, that's already very well established. COPD refers to chronic obstructive pulmonary disease. These would be lung conditions, diseases where airway is being blocked. And in COPD research, in COPD rehabilitation, the higher the VO2max, the better is the prognosis, is the disease condition, that the chances of this person being able to live with the disease with a better quality of life is associated positively with VO2max. The same thing, the results of cardiac rehab is also positively associated with VO2max. So for heart patients, if you have gone through a heart bypass, you put a balloon in the heart, when you're going through the rehabilitation process, VO2 is one of the very useful measurements to see how well this person has recovered and how well this person will continue to function normally in their daily life. For heart transplant, VO2, the heart transplant is for people where the heart is already failed. So in order to survive, you got to change the heart from another person. And VO2 is being used as one of the criteria for deciding whether is the patient suitable for heart transplant. It's the opposite. Heart transplant is only suitable if your VO2 is very low, meaning that VO2 is being used to demonstrate that, you know, the chance of this person surviving is actually quite low. And because of that, it's better for this person to undertake a heart transplant. Okay, so as you can see, from sports and physical performance, VO2 has extended to many areas of clinical practice in public health and so on. Two very broad areas. I believe everywhere in the world, you face the same problem in Singapore, Asia as a whole. Asia is aging very quickly. There's a very large aging population that's going to hit Asia in the next 50 years. And these are the two main set of conditions that comes along with a very high aging population. Metabolic syndrome, these are the metabolic diseases on the left here, and on the right, mental conditions, where as we age, our hippocampus size gets smaller, and hippocampus size is associated with memory. So people with Alzheimer's, for example, their hippocampus size is shrunk to very small. Dementia is another form of memory loss, and then you have depression. And as we get older, you find that the way we walk, the way we perform complex tasks, it gets more difficult. And VO2max, having a high VO2max has been shown to be able to be protective of elderly people. Firstly, from developing these conditions, for those who already have these conditions, to be able to slow down the progression of the disease, and in some cases, to stop the progression of the disease. So these are the application of VO2max in health, in public health, in chronic disease and aging health. In sports and occupational setting, right? If you work in occupations that require you to exert yourself physically, VO2max is something, VO2 or VO2max is something that is used, in the last 50, 80 years already. So I did, as I said, I did research on soldiers for 20 years, and I do a lot of VO2 measurement, which was very helpful for me. So one of the important things that VO2 does is that it gives a very objective measurement of work. How much physical work is needed to perform that task? How much work has already been done? So whether I'm training or I'm trying to assess whether is this person suitable to be a policeman, to be a soldier, is this person supposed to be undertaking a very demanding work task, I can use VO2 to quantify the demand of the work. And then I test his VO2 to see whether can he match the demand. Okay. Training needs and adaptation effectiveness, and this is very much applied to athletes, right? If we are training an athlete, if you know that if you know that people who perform well have this amount of VO2, and you measure your athlete, his VO2 is at another standard, it gives you the VO2 differences, gives you a very good idea of how much adaptation is needed for this athlete to be able to match his or her competitor in terms of aerobic capacity. Also, as you train, when you have to measure effectiveness of your training in terms of VO2, in terms of aerobic capacity, VO2 is a very good measurement, and especially for endurance sports, cycling, swimming, running, even for sports that short bursts, that open chain sport like soccer, rugby, and so on. VO2, having a high VO2 max is important. So as you train, as you start your season, you do a baseline measurement. As you train 6 weeks later, 12 weeks later, you measure VO2 again. It gives you a very good indication of how much improvement has taken place. The next one is in TID, talent identification and selection. So one of the things that is different between mass participation sports and elite sports is the person. It costs a lot of money and time and resources to develop an elite athlete, right? And before you even decide to select the athlete for development, one of the things that you try to do is to identify whether is this person talented or not. I will tell you now that around the world, people have been trying for the last 50, 60 years, have a set of measurement to predict performance, to predict potential for elite sports. None of those have worked. Whether you're talking height, weight, body shape, body size, and so on, none of those have worked because the performance at elite sports is too complex to be able to be predicted by, just by those few parameters. But if you're talking about endurance sports, right? Marathon running, 10K race, 5K race walking, cycling, and so on, pure endurance sports. VO2max is a very robust way of identifying the potential of your athlete. So people who participate in international endurance sports, 10K races, marathons, and so on, the level of VO2max is not something that anyone can train to achieve. You got to be genetically designed. You got to be born with the genes to be able to achieve that level of VO2max. So being able to measure VO2max helps you in having that ability to identify endurance athletes. Functional capacity, work performance, and tolerance. And this is something that can assess whether can your athlete improve further. You train, you measure, you train, you measure. And if you see that after training, they're plateaued, perhaps you need to change your training method, right? And VO2max is a way for you to assess that. In research, VO2 gives you very useful indicators of metabolic functions. You have all studied pathway. It gives you an indication of how well your metabolic pathway is functioning, and also your lungs are working together. This is a background that I'm giving you before we go into the actual content on VO2max, just to help you to appreciate where it started and how the application of VO2 now in different aspects of sports, occupation, and clinical setting. Now, many of us look at VO2 as something we measure from our expired air. And we look at VO2 as something that we measure, as something that we're trying to measure in terms of measuring the heart and the lung function, like what I said just a few minutes ago. But what I want to impress upon you really, when you look at VO2 or VO2max, you look beyond the heart and the lungs and the muscle. You got to look at the cell, because this is what VO2 is trying to measure. Okay, let me explain. Yeah. So this is the metabolic pathway. I'm sure many of you are familiar with it. This is my version of it. This is one muscle cell. And within the muscle cell, there's one element called the mitochondria. So behind this line would be the mitochondria. Outside this line would be the cell itself, outside the mitochondria. And in your metabolic pathway lesson, you have learned that outside the mitochondria, energy is produced by the anaerobic system, right? So we have the stored ATP there. When you start exercising, you start using stored ATP first. And then the next level will be ATP coming from your creatine phosphate. But the main engine for producing ATPs in your muscle would be glycolysis, isn't it? But this is anaerobic. It doesn't use oxygen. So at the end of glycolysis, you get a net gain of 2 ATPs. But the more important thing is you get 2 pyruvate unit, right? And these 2 pyruvate crosses the mitochondria and goes inside the mitochondria, and it goes into this circle here. Some call it Krebs cycle. I call this citric acid cycle. They refer to the same thing. The Krebs cycle produces 2 things, that's all. It produces CO2, so this is one area in the body that produces. The other thing that it produces is hydrogen ions, right? And these hydrogen ions are then transported down the the electron transport chain. Okay, and as it goes down the electron transport chain, you get ATPs being produced, and the ATPs are then used to produce energy. Right? For 1 unit of glycogen that goes into the ETC, we get about 36 ATPs. I'm sure you've done that in your lesson. But my purpose today is not to talk to you about metabolic pathway, but to help you to see how to connect, help you to see the connection between VO2 measurement and the metabolic pathway. So as the hydrogen ion come down the electron transport chain, this hydrogen ion has to be moved away, has to be removed from the cell, because otherwise when you have a traffic jam, if it doesn't get removed, you have a traffic jam that will slow down electron transport chain, it will slow down the Krebs cycle, that will slow down the acceptance of pyruvate over here, and your work has to stop. As you have to slow down, it has to stop. And the body has a very interesting way of removing hydrogen ion. It matches this with oxygen that's coming into the cells. So we breathe in oxygen from the air, it goes into the blood, the heart pumps the blood to the muscle extracts the oxygen comes into the cell, and it comes in the cell, it meets hydrogen ion here, and they pair up, and it forms water, right? And that water is then removed from the cell. And because we have this process of forming water, we can continue to run marathons, we can continue to run 100-kilometer races, 200-kilometer races, because as hydrogen ion comes down, oxygen is coming in, converting it to water and removing it from the cell. And this is how energy can be expanded, right? The longest race I'm aware of today is 200 miles, is 300 kilometers, and they do that without eating food, yeah? Now, two things I want to highlight over here. The first point I want to bring across is this. Although this metabolic pathway inside the mitochondria is referred to as aerobic metabolism, right? For the last 80 years, 100 years. Oxygen is not involved in the production of aerobic energy, right? Where is ATP produced? Energy is produced here in the electron transport chain, isn't it? And up to this point, oxygen is not involved. Okay, so oxygen is not involved in the production of aerobic energy. The role of oxygen is not in energy production. The role of oxygen is in clearing, removing hydrogen ions from the mitochondria so that this system can continue to work, and hydrogen ions can continue to flow, and ATP can continue to be produced, so that you have energy, you can continue to do your work for a long time. And this is where, you know, it's important for us as sports science students to appreciate the role of oxygen, right? To understand it correctly. Okay, it is because of that, because it's able to remove hydrogen ions, we're able to continue working for a long time. Now, the second point I want you to understand is this. So as oxygen comes in, right, it removes hydrogen ion. Now, assuming now you run faster, you're running at a certain speed, you run faster. How does your body produce more energy to allow you to run faster? This system has to work faster. At every minute, there'll be more hydrogen ions coming down. And in order to clear this, you need more oxygen to come into the cell to remove the hydrogen ion. Then you run faster some more. Then more oxygen need to come in to remove the hydrogen ion from the mitochondria. And you increase your speed even further. And every minute you get more hydrogen ions coming in, more oxygen need to come in to remove hydrogen ions. You come to a point where no matter how much more you increase, how much more faster you run, you cannot increase the cells anymore. Okay? And this is the point we call VO2max. I want you to understand that when we say workload in this, you know, an increase in workload, an increase in oxygen uptake, this is what happens inside your cell. All right. And when we say VO2max, this is what happens inside your cells, in that you can't increase the oxygen supply to your cells anymore. And because of that, you can't bring down hydrogen ion, produce energy at that rate anymore. The only way you can continue working is to slow down your work. All right. So this is the only a complicated slide. I promise you, after this, it'll be a lot easier. Okay, so that's the background. This is why there's a linear relationship between oxygen uptake and workload. The more intense is your work, the more oxygen you need. And it comes to a point where no matter how much more you work, you can't increase oxygen uptake anymore. So I thought I just want to define the different terminologies that you come across. So VO2, of course, is volume of oxygen consumption. VO2max is maximum volume of oxygen consumption. In the last 10, 20 years, there's a new term that came about, that's VO2 peak. And some people use VO2 max and VO2 peak like they're the same thing, but they are not. Let me explain to you. So as I said, right, VO2 max, right, is when as your work intensity increase, your oxygen uptake will increase, and you'll come to a point where no matter how much more you increase, you cannot increase your VO2 anymore. And that's what we call VO2 max, right? So this is the concept of VO2 max. Now, this is a very beautiful line, but unfortunately, our body is not designed that way. In my 30 over years as an exercise physiologist measuring VO2, I've never seen such a beautiful line. What you see is more like this. Okay, this is the real line that you see when you measure VO2. And if you're trained, if you're experienced over here, in all this, you'll still be able to see where the plateau takes place and define your VO2 max. But some people have trouble defining VO2 max. And what they do is that they take the highest point of VO2 and they call this VO2 peak. So this is the difference between VO2 max and VO2 peak. VO2 peak is one single point, the highest point of VO2 of oxygen uptake. VO2 max is a trend, right? Showing a plateau in oxygen uptake. And this is the big difference, okay? Because VO2 peak may not represent your VO2 max. It can be just that you take a deep breath, a sudden deep breath, or you breathe a few more breaths in that few seconds and you get a peak, artifact like this. Having said that, if you're working with people who are unfit, people who are obese, people who are during rehabilitation, they will not be able to achieve VO2 max because the other parts of the body will limit the achievement of VO2 max. And for those population, the best that you can use is the highest oxygen uptake of the VO2 peak. So VO2 peak will be useful for populations that are unfit, that are unable to achieve VO2 max. But most of the time, you're working with people who are fit, who can exert themselves maximally. You will try to look for VO2 max. VO2 itself is basically the entire range of oxygen uptake, right? Just like you say heart rate max, sub-maximal heart rate, 70% heart rate. All these are heart rate, right? So VO2 would be the same, right? The entire range of oxygen uptake will be VO2. We classified VO2 from resting all the way to maximum. I just want to quickly show you the real data that I have. I measured in one of my study subjects. So we had him run at 8 kilometers per hour. Then we increased the speed 2 kilometers to 10, to 12, to 14, to 16. At 16, he could go on some more. We increased the speed, the gradient by another 5% or so. And then then he got exhausted. We rested him for about 5 minutes. And then we did a supra maximum exercise, a second round at starting at about 16 kilometers per hour. And then we ramp up the speed again, just to confirm whether did we get a VO2 max, to make sure that he did exert himself maximally. So what I want you to see is the linear increase in oxygen uptake as workload increased. And even though it's messy, we were able to identify a plateau over here. So his VO2 max was about 58 mils per kg per minute, right? And then he rested and we tried again. We pushed him maximally. We went from 0 to 16 kilometers per hour. Every minute we increased 5% gradient. He could only last slightly more than a minute. And he got 60 mils per kg per minute. So this was very good. It shows that he has reached his maximum. And what I'm trying to show you here is even in this kind of data, you can see plateaus where you can identify VO2 max. And in this case, if I were to use VO2 peak, it will be this point over here, the highest VO2 measured. that will be 62 meals per kg per minute. All right, so just to give you an example of the concept I just spoke about. So we come to measurement of VO2 max, and then I want you to understand, right? Just now in the energy pathways slide, I showed you the metabolic pathway, and metabolic pathway is about energy production, and that measurement is called calorimetry. When you measure energy expenditure, you're performing calorimetry, and when you do VO2, actually the main purpose was to quantify work using energy expenditure. How much energy you're expending per minute, okay? This is the most accurate way. It's called direct calorimetry. You would exercise inside a room and there'll be water flowing through the room. And because when you exercise, you produce energy, you produce heat, and that heat would change the temperature of the water flowing through the room, and using that, they calculate energy expenditure. But as you can see, it's something very difficult to do. You've got to produce a lot of heat to change the temperature of water flowing through the room. So this is actually the most accurate way. It's called direct calorimetry, but because it's hard to do, we use expired air to measure VO2. And this is why expired air measurement of VO2 is called indirect calorimetry, because you're not really measuring energy expenditure. You're measuring oxygen uptake, and you're using oxygen uptake to estimate energy expenditure. And this is something that sports science students, I think, because VO2 is used so frequent, sometimes we forget that we are actually measuring something indirectly, okay, when we measure a VO2, all right? So the energy expenditure calculated from VO2 is an estimated amount, and that is why this is called indirect calorimetry. So it is the principles of indirect calorimetry is based on oxygen delivery, right? Now we can't measure the cells, what's going on in the cells. And so the physiology of indirect calorimetry is based on the Fick equation over here as a definition of VO2. And the Fick equation says that VO2 is a function of two things, right? One is your cardiac output. Cardiac output is how much blood your heart can pump out per minute. So how much blood your heart can pump out a minute, and that will be how much oxygen your heart can pump out to your muscles every minute, right? Multiplied by here, arterial venous O2 difference. Artery is what you deliver to the muscle. Vein is what you receive after the muscle has extracted the oxygen. So what you deliver minus what is left in the blood would be what you utilize, isn't it? So if I deliver 10 mils of oxygen through the artery, on the veins, I only have 5 mils left. That means I use up 5 mils of oxygen, okay? So essentially, VO2 is a function of how much your heart can supply, multiplied by how much is extracted in the muscle. Okay, so that will be your cardiovascular system, that will be your muscle cells and your blood flow within the muscle itself. So there are all these factors that will influence your cardiac output. I don't have time to go into them today, but if you go into your cardiovascular physiology, essentially anything that influences your stroke volume and your heart rate would influence your cardiac output, right? And this is oxygen delivery. On this side, right, inside your muscles, these are the different factors that will influence how much oxygen your muscle can extract, can remove from the blood that's coming into the muscle. Okay, and how much that can be done will determine how much oxygen is being utilized. So I just want to point out from here two important things, yeah, for the muscle. One is vascularization, how much blood vessels there is in your muscle. Two is the number of mitochondria you have in your muscle. As you train, because of the need to extract more oxygen, your muscles will generate new blood vessels, and your muscles will generate new mitochondria. And this is one of the adaptations that take place that allows us to have a higher VO2. But the main thing I want to share with you here is that if you think about VO2 physiologically, you need to think about oxygen delivery and oxygen utilization. How much oxygen you can deliver to the muscle and at the muscle, how much oxygen your muscle can extract and use it to produce energy aerobically. Okay, and that comes down to your cardiac output and your AVO2 difference, right? Okay, but you know, when you're trying to measure VO2, you still cannot measure cardiac output. It's very invasive, isn't it? You can't put a catheter into the heart and artery and expect this person to be exercising maximally. And that is why, for the same principle, the Fick equation, we have metabolic carts. These are the machines we use to measure VO2. And the machine uses expired air. Okay, and I want to explain how that works to you. All right, so in indirect calorimetry, the whole idea is to look at the difference between what you inspire and what you expire. Okay, so this is air from ambient air. It contains 21% oxygen, 0.03% carbon dioxide. The rest are nitrogen. When you breathe in the air goes into your lungs. From your lungs, your blood picked it up, gets delivered to your heart, and from your heart, it pumps the oxygen to the muscle, isn't it? We just talked about that, cardiac output, right? And these are all on the arterial side of the blood circulation, where the blood is oxygenated. Okay, so oxygen coming in from the atmosphere goes into your lungs, goes into your blood, and the heart pumps it to the muscle. And within the muscle, the oxygen then gets transported to the mitochondria. And on the other side, the venous blood side, the blood that flows out of the muscle, again, whatever that remains, oxygen that remains here, will then be pumped out from the muscle back into the blood, and then the cardiovascular system will then push it back into the lungs, and then you expire it into the atmosphere. There's another place here that produces gas, right? We say that the metabolism Krebs cycle produces CO2, but there's another part. Remember, there's lactate production as well. So when your muscle produces blood lactate, right, it goes into the blood. And when lactate goes into the blood, lactate is acidic. And the body has a very nice system of controlling the acidity of the blood, the pH of the blood. When it gets too acidic, right, the body buffers it with sodium bicarbonate, same as your baking soda, right? It is an alkaline, so your body produces an alkaline to counter the effects of lactate, so that the blood pH is maintained. But what's important is this: by buffering lactate, it produces more carbon dioxide in the blood, and that carbon dioxide adds on to the carbon dioxide that's already in the blood, right? And this is where lactate buffering happens. If you're running very hard, and at some point you start to breathe very hard. It's because of lactate buffering and carbon dioxide produced from carbonic from this process. Okay. In any case, so the gases from the blood and the gases, the CO2 produced by lactate buffering, are then pushed out to the lungs, and they go into the expired air. So the machine that you use to measure VO2 only does two things. It knows what's the air coming in, how much air, how much oxygen, CO2, and all comes into your body. It measures what comes out, right? The difference that between what goes in and what comes out, you get VE, which is minute ventilation, or your air volume. You get VO2, which is your oxygen utilization, right? What you breathe in minus what you breathe out is what you use, isn't it? And then you get VCO2, volume of CO2. That will be how much CO2 you have produced, right? You have added more to what is over here. Okay, so essentially that is the whole concept of measuring VO2. Fundamentally, you're looking at this. So VO2 is how much FiO2 refers to inspired oxygen. Okay, inspired oxygen, and that's 23.9%, multiplied by the volume of air you inspire, minus the oxygen that you expired, multiplied by the volume of air you expired. So simple, right? What you breathe in minus what you breathe out. And remember, you breathe in so many liters of air, and in each liter, there's so many percent of oxygen, and that's how you come to calculate the actual oxygen content. Okay, I'll finish this slide, then I'll take a question. So there are two units of measurement. One is liters per minute, and the other one is milliliters per kilogram per minute. They are used for two purposes. One is that, now when you say liters per minute, it doesn't account for differences in body weight. So if I'm 70 kilogram, someone is 80 kilogram, he would have more muscle cells in this person. He will have more muscle cells, right? So it's not accurate to compare two person of two different body weight. And so when you divide this amount by the body weight, you get milliliters per kilogram per minute. So it doesn't matter what's the body weight, you're measuring VO2 for every kilogram of body weight. So this is one way to control for differences in body weight. The other purpose of having these two units of measurement is to measure them based on the different type of work that you do in measuring VO2. So in running, we will use meals per kg per minute, because in running, you carry your body weight over a distance, right? And that determines your body weight times the speed that you run determines how much energy you need to move your body over the distance at that time. And therefore, that is why when you measure VO2 using something that carries the body weight, you need to use this unit of measurement, meals per kg per minute. In cycling ergometer, your body weight doesn't drive your VO2. Your VO2 increases, the workload is driven by the resistance at the bicycle, at the pedal of the bicycle. Okay, so because of that, you don't need to account for body weight. You account for volume of oxygen uptake as a whole, right? So as you increase your resistance on the bicycle from 50 watts to 100 watts, oxygen uptake will go up. From 100 to 150 watts, oxygen uptake will go up, right? And that and independent of body weight. So I'll just give you an example here. Subject A, 60 kilogram. If we measure liters per minute, it's 3 liters. When you divide, we convert liters to milliliters, you times 1,000, that's 3,000 milliliters. You divide by 60, you get 3,000 divided by 60, you get 50 mils per kilogram per kg per minute. Subject B, 70 kilogram body weight, same, 3 liters per minute of VO2 max, right? And to convert to this, you divide 3,000 by 70, you get 43 mils per kg per minute. So this is, in this example, what I want to show you is the reason why we use mils per kg per minute. Firstly is to compare between two people with different body weight. Secondly is to account for the role of body weight in as part of the workload in when you do exercises that carries the body weight from point A to point. Okay, I think I will stop here for a while and I'll take question.
Okay, so it's time for a question and answer?
Yeah.
Okay, so anyone who want to asking directly, or you can write in chat. Hello? Anyone want to asking? Maybe they still looking. Hello?
Yeah.
Everyone can write in here if anyone want to asking something, or you can asking directly to Professor Fabian Lim.
Yeah. If there are no question, I can just continue and then
okay.
You can reserve your question for at the end of the.
You can continue so they can. Ade Bagus Pratama want asking something. Okay.
Okay, good. Yeah.
Okay, please, Ade.
Thank you for this occasion, Mrs. Titin.
Thank you.
And Professor, I'd like to ask you about the increase of the rate of breathing, because of we have to remove the carbon dioxide, right? And
yes.
my question is, this increased the rate of breathing comes from the increase of carbon dioxide, or we have to increase the oxygen supply demand?
Okay, that's a
as I know, if we increase our effort when exercise, and then it will affect on the respiratory rate, right?
yes.
And then the higher respiratory rate will increase the work of breathing, and it will affect on the main muscle to work. So, I mean, if can we increase the oxygen supply by like additional oxygen, like oxygen 8?
Yeah.
It can be useful for improve performance.
Okay,
Thank you.
great. Thank you. That's a very good question. I'm glad you asked. So the question is, firstly, when we exercise, our breathing rate, right? Is it driven by the lack of oxygen, or is it driven by having too much carbon dioxide in the body? That's the first question, if I understand it. The second question then is that, is there a way to increase oxygen uptake through other forms of intervention? So the first question first. The drive to breathe comes from an overload of carbon dioxide in the body. Doesn't come from the lack of oxygen. Okay, that is what that drives us to breathe harder, to remove carbon dioxide. That's because of the nature of how the respiratory system works. And number one. Number two is that I will show you in another slide later the direction of movement of the gases in the lungs. Yeah, that's the first one. So it's driven by overload of CO2. And the only way to overcome that, right, meaning that you want to have less CO2 so that you can exercise harder, is to increase your VO2max. Because if you have a higher VO2max, then you produce less lactate, isn't it? For the same workload. And with less lactate, the buffering doesn't exist so much at the same workload, right? The buffering, you get more buffering at a higher workload. Okay, so from a training and physiology point of view, the way to delay that threshold where you need to breathe very hard due to an overload of CO2 comes from an increase in VO2max. I hope that answers your question. Yeah, other than that, I do not know of any other way to increase oxygen output other than training stimulus. Yeah, I'm not aware of that. Of course, there are ergogenic aids, right? People do blood doping and things like that, but those are illegal. Yeah, and they have consequences on the body. Yeah. Okay, shall we continue and then I'll stop for question again?
Okay, so anyone again want asking something from Hiras? Hiras, you can ask him directly or I can help you. Hiras? Okay, Hiras is asking about the role and implementation of mental health on the level of sports achievement. Just like that.
Yeah, so there's quite a lot of evidence now on the benefit of sports participation, fitness, and in mental health in both young and older people as well. So in younger people, it's been found to be helpful in terms of cognitive function, mathematical performance and things like that. But I'll say that in those studies, the control is still not very well controlled, so there may be some error in those results. But in older people, definitely sports participation, physical activity, and mental health is very well studied. And the benefits of physical activity and fitness for good mental health is well proven. Yeah. Okay.
Okay. Thank you, Professor Fabian.
Yeah.
Okay, you can continue to next slide.
So I'll just continue with the lecture, and then if you have a question, we can see have a chance to do that at the end of the lecture. So I now come to the process of testing, testing VO2. Now these are the different protocols that I learned as a student in 1980s. Now you know how old I am. When I was in university, these are different protocols that were taught to me, but they are no longer used nowadays. I just show you, just to let you know where I came from, the dinosaur. So nowadays, we use what is called a relative protocol, test protocol, okay? Ability-based, based on the ability of the individual. So rather than have the same protocol for everyone, we adjust the protocol to each individual's fitness, each individual's ability. So when a person come to my lab, I will ask about their running time. I will ask, for example, what is your 5K running time? What's your 10K running time? If they don't run so far, even the 3K, 3 kilometers running time. Based on that, I estimate what is their steady state running speed, right? If you're running 5 kilometers in 30 minutes, then I know that you're running at about 6 minutes per kilometer. That's your running speed, okay? And I will start my running speed, we're talking about treadmill here, at 1 to 2 levels below the steady state running speed. Okay, so if your running speed is 6 minutes per kilometer, I will start it at maybe 8 minutes per kilometer, and then next stage is 7 minutes per kilometer before I come to 6 minutes per kilometer after 3 stages of increasing the speed. Everyone okay with that? Yep. Okay, so and depending on the speed that you're at each stage, you can increase by 1 to 2 kilometers per hour or 1 to 2 minutes per kilometer, depending on how you calculate the speed, right? Some use kilometers per hour, some use minutes per kilometer. Okay. Now, whether you increase by 1 or 2 kilometers per hour or 1 to 2 minutes per kilometer, the important thing is that with the increment, you should be able to see a noticeable increase in VO2, right? Then only it allows you to see that change in VO2. So the increase in speed should be based on how much change in VO2 you want to see at each stage of your protocol, okay? The other thing is, be careful not to increase too much, because you increase too much at each stage, you won't get a true VO2max. The person will get exhausted before they reach their VO2max, right? So usually it's about 1 to 2 kilometers per hour or 1 to 2 minutes per kilometer. Now, how much time per stage? The time that you keep to one's running speed should allow you to see a steady state VO2. Okay, so when you change, let's say, for example, from 8 minutes per kilometer to 7 minutes per kilometer, the time that they stay at each stage at 7 minutes per kilometer should allow you to see a steady state VO2. So at every speed, you should be able to see a steady state VO2, right? When you just change the speed, when you go from one speed to another speed, right, there will be a fluctuation in the VO2. The first few seconds will be very messy. And you need the time to be long enough so that you're able to allow VO2 to stabilize, so that you know that at that speed, this is the amount of VO2 that the person is incurring. Okay, and usually you try not to have more than 6 stages. You try to get VO2max in about 4 to 6 increase in speed, increase in speed. And the test should be about 10 to 15 minutes to get the VO2max. The reason is that doing too many stages or going too long, you cause the person to get exhausted before they can achieve the VO2max. So it's a balance between speed and duration. Okay, 4 to 6 stages, about 10 to 15 minutes. So about 2 to 3, sometimes 1 to 2 minutes per stage. Okay, so besides VO2max, you can use the same protocol to test for running economy. So running economy is very important for running performance. Running economy refers to how much energy you need to use to run the same distance. And that this comes down to your technique, your running techniques and your physical structure, your anatomy and so on. So if you're very economical, you will need less energy to run the same distance, to run at the same speed, okay? And that can be tested using the same test protocol. VO2 speed prediction, right? You want to know, so if you're testing VO2, you want to know if in the field I'm running, let's say at this speed, what is my VO2? So in your athlete, right, you can bring them to the lab, you run the VO2 at different speed, you record the VO2 so that in the field, when they run at different speed, you know that they're running at so many % of their VO2 max. Okay, so these are the different things that you can do to test for VO2. Now, one common protocol that people use is called the REM protocol. So again, you start about 1 to 2 stages below his steady state. And then every minute you increase the speed by 1 kilometer per hour. Okay, so you keep increasing the speed until they achieve VO2 max or until they reach exhaustion. They cannot continue anymore. So this is used in some studies. Usually for people who are not so well trained, this protocol may lead to premature exhaustion. So this is more suitable for people who are well trained, okay? Another protocol is what I said here, the running economy protocol or the VO2 speed protocol, where same thing, if this is the, if this is your steady state running speed, you do about 1 or 2 speed down, and you maintain about 1 to 2 minutes per stage. And then you increase, right, by about 1 to 2, the speed, 1 to 2 kilometers per hour per stage, depending on your protocol and on your subject. And you do that until about 14 to 15 kilometers per hour, and then you increase at the speed of 1 kilometer per hour per minute, okay? So for example, if my steady state is about 10 kilometers per hour, for example, my running speed, I will start here at 8 kilometers per hour for 1 to 2 minutes, then 9 kilometers per hour at 1 to 2 minutes, then at 10, then I'll go to 12, then I'll go to 14 kilometers per hour. After that, right, because already the protocol is dragging quite long, increase the speed by 1 kilometer per hour every minute. This is the protocol I use. I call it the Lim's protocol, and you're free to copy it if you want, if you find it useful for you. I find it to be quite useful for quite a wide range of training state, yeah? From those who are moderately trained to those who are highly trained. So the first 3 speed, 8 kilometers per hour to 12 kilometers per hour, is 2 minute. There are 2 minute stages, and I take this as warm-up stages. And because they are longer stages, I'm able to see the running, the stability in the oxygen uptake and the speed as well. After 12 kilometers per hour, I increase by 1 kilometer per hour speed every minute until 16. Okay, after 16 kilometers per hour, I don't increase in speed anymore because the legs cannot move so fast for some of the athletes. So what do? I increase the gradient of the treadmill by 5% every minute until exhaustion. And usually, even for very highly trained, I'm able to get VO2 max at about 16 plus 10% for the very highly trained. For not so highly trained, I'm able to get VO2 max at about 15 to 16 kilometers per hour. Yep. Okay, so this gives you an idea about protocols. And again, this was what I showed you earlier. I won't repeat that again. Yep, these are the 2 plateau points that I showed you earlier to get the VO2 max. Okay, I want to talk a bit about now another set of measurement you can use from VO2 max test that can be useful for you when you're doing VO2 max test. And these are your ventilatory threshold. So just to remind everyone again, when you do your, in the energy pathway, at the end of glycolysis, there are 2 pyruvate units. Now, when you get more pyruvate unit that can go into here, you get a lot of pyruvate unit produced, and more than what the mitochondria can accept. You get extra pyruvate floating around here. And the body needs to clear away the pyruvate because otherwise it will slow down your glycolysis and that will slow down your work. And the way it does that is by converting pyruvate to lactic acid, okay, in the muscle. And that lactic acid is then transported out of the muscle into the bloodstream, like we talked about earlier. And in the bloodstream, you get buffered, it gets neutralized, the acid get neutralized, and you produce CO2. That's the main point I want to remind everyone again. Then that brings me to my next slide, okay? What other things can you make use of in VO2 measurement besides VO2max? Okay, and this is one measurement you can use. It's called ventilatory threshold. VE refers to minute ventilation. This is the volume of air you expire every minute. Okay, so as you increase, at rest, our VE is about 10 liters per minute. So right now, all of us resting, we are expiring about 10 liters of air every minute. At maximum exercise, moderately trained will be, you can increase by about 12 times to about 120, 150 liters per minute. In very well trained, you can go up to 180 liters per minute. So the lungs is very flexible. You can increase the volume by 12 to 18 times, of air exchange. But the main point is this. So as you exercise, your volume of air intake will increase, right? Because you need to bring in more air into the body. Because you bring in more air, you need to expire more air. So minute ventilation will increase as your intensity increases. You come to a point where you see an inflection, you see a sharp increase in minute ventilation, okay? And this is the point where we talked about just now. Where there's buffering of lactic acid, there's a lot more carbon dioxide in the blood, and therefore you need to breathe harder, and you produce a lot more air every minute. And this is the inflection point. It's called ventilatory threshold. It is one way to estimate the point or your exercise intensity where fatigue starts to occur, where exhaustion starts to occur. Some would try to use this as an estimate of your anaerobic threshold, but there's some problem with that, okay? But as an estimation of the point where exhaustion will about to start, it can, some coaches, you can use this as one of the indicator. Yep. So another indicator is VE, VO2. So again, VE is your air production every minute. VO2 is oxygen uptake every minute. Now, when you reach VO2max, right, your denominator, your VO2 will become plateau. It won't increase anymore. When you reach VO2max, that's the point your body produces a lot more lactic acid. That's the point you buffer more lactate and more CO2 is produced. So your denominator will remain constant. Your numerator, this number will go up sharply, right? So you also get an inflection point like this. And this is another indicator that you can use from your VO2 measurement to indicate the point of exhaustion. Okay, these are what we call ventilatory thresholds. Another measurement is VE, VCO2, and because VCO, this is production of CO2, this is air volume, both will increase together, so you won't see a sharp increase. And this is a good indicator to use as a baseline, right? VE, VCO2 will increase slightly or stay about baseline, and there's a departure of the other two indicators from here. And this is the point where exhaustion is likely to take place. So if you're training, if you're a coach, you want to train just below the threshold. Similar concept as the anaerobic threshold. Yep. These are different things different ways you can make use of the data that you derive from VO2 measurement, right? So if your workload on this side, you have VO2 on this side, you can use it to estimate your work capacity. So by measuring VO2max, I know how much you're able to do at that particular point in time. When I train the person for a period of time, I see whether is there a change in VO2max and how much improvement has taken place. And at some point, when I keep doing the same training, I won't improve anymore. My VO2max won't improve anymore because the stimulus is the same. I need to change my training intensity, my training methods, and so. And VO2 is a good way to do that, right? When your VO2 starts to plateau, you're not improving anymore, then you know that you must change your training prescription, you must change your exercise prescription for VO2 to go further. Now, one of the things that's difficult in measuring VO2 is that, you know, you measure VO2 in the lab, then you go to the field, you can't measure VO2 in the field. And one of the things that's very useful is to look at the relationship between VO2 and heart rate, so that you know that at certain heart rate is equals to so much of VO2. Okay, and in the VO2max test, you have both heart rate and VO2 measurement, right? You can look at that relationship and use that to estimate VO2 in the field using heart rate. So if you're a coach, you are training someone in the field, you know, if you have done the VO2 measurement, your heart rate data will become a lot more meaningful for you other than a pure heart rate measurement. It is an estimation of your VO2 as well. We talk about VE, ventilatory threshold just now. Okay, so like I said, if you don't have the ability to measure lactate, if you don't have the opportunity to measure lactate, minute ventilation or ventilatory threshold can be an alternative. The next best thing to do to estimate when does exhaustion takes place, and the training should then take place just below the ventilatory threshold. The same application if you use VE, VO2, like I explained in the slide before this. The next one is to look at work intensity. Okay, so if you have workload over here, and you know, if you have RPE. RPE is the rating of perceived exertion over here. And you know that at some point your RPE becomes very high, meaning you rate that you are exerting very hard. And that's the point you define as work failure. Okay, beyond that, you cannot increase your workload anymore. And you look at VO2 at that point, you can define the VO2 or the workload where you start to fail. And this is very useful for exercise prescription because you know your limitation or you know your baseline. Then from there, if there's a change, you know how much improvement there is. Finally, you can use VO2 to estimate your fuel utilization by looking at RER. RER is you divide VCO2 by VO2, you get this respiratory exchange ratio, right? How much CO2 you're producing over how much oxygen you're utilizing. So an RER of 0.7, indicates that you're using mostly fat in your energy. As your work intensity increases, right? As workload increases, your RER will move towards 1. When your RER is 1, you're using dominantly carbohydrate as your fuel. Beyond 1, you're moving towards the point of exhaustion. That means you're in a zone of anaerobic metabolism. Okay. So if you're helping someone to lose weight, or if you're strategizing your marathon, okay, you want this person to be running at the intensity where they're utilizing so many, you know, the distribution of fat and carbohydrate and so on. Using RER can help you to get that kind of estimate. So these are just different applications that you can use for VO2 that I hope that can be useful to you. The next set of my lecture, I'll be showing you some data from research and then to draw some lessons from there. This is a set of data that was collected by Sid Robinson as far back as 1938. And he measured VO2 of average men and women and compared that to elite male and female runners. And you can see this is the average women. As age increase, there's a decrease in VO2. And that's because of deterioration in cardiac output and deterioration in muscle oxygen utilization, extraction of oxygen at the muscle, right? However, if you look at elite male and female athletes, they remain quite consistent, at least up to about late 30s or so. At this point, not many of them do elite sports beyond 30 years old. Okay, but you can see that from here, there's deterioration, whereas in elite males and females, there is a maintenance of VO2max. So training stimulus can help to maintain VO2max over a longer lifespan. The second lesson from here is to understand the difference between male, female in terms of endurance performance. that there is an advantage of males over females when it comes to VO2 max. I will explain that later when we talk about respiratory physiology. For now, just bear in mind. One of it is because of body composition. For every kilogram of body weight, the male have more muscles than female. Females have more fat because of the way the body is designed. So more muscles mean there are more cells to utilize oxygen, okay? The other one has to do with red blood cells. Males have got more red blood cells in the body and therefore carry more oxygen for every liter of blood. These are measurements taken in 1965, Norwegian women. Again, you can see a difference between average untrained male, female, and male and female athletes. That training can make a big difference in the VO2 max or the capacity of an individual. Now, there are no international norms on what is high, what is low in terms of VO2 max. But what I try to do in this slide is to give you a sense of how to categorize VO2 max. Now, as I said, this is not based on any deep research or so. This is based on my past 30 over years of measuring VO2 max and reading and understanding VO2 max. Okay. So at resting, our VO2 is about 3.5 to 6 mils per kg of body weight per minute. And elite endurance athletes, we can go up to about 80 over mils per kilogram per minute. Okay. And I just want to explain some of these differences to you. Now, this part, elite athletes 70 to 80, and even some part of this competitive athlete, when you get nearer to 70 or so, you need to be genetically, you need to have the genes in order to have this kind of, in order to train to have this kind of VO2 max. An ordinary person, no matter how we train, it's quite hard to go beyond 70 mils per kg per minute. Yeah. Most of the time, an ordinary individual who don't have, with ordinary genetic makeup, if you train very hard, your VO2 max is in the high 50s and in the low 60s. Okay, and this is why VO2 max is very useful for identifying talents for endurance athletes. Marathons, cycling and running are the two sports where VO2 max is very well established. Okay, so this is one way to determine whether is this person designed for elite sports or not. All right. So elite endurance athletes is about 70 plus to 80 plus VO2 max. So if you measure VO2 max of Asian Games marathoners or Olympic Games marathoners, this would be the level of VO2 max you're looking at. For competitive young athletes, okay, if you're relatively young and you're competitive, you can get VO2 maxes of about 60 plus to about 70 or so. So like I said, this is where there's a mix between those who train very hard, not so genetically inclined, and those who are genetically inclined and train hard as well. Okay. Beyond that, if you're young and active, like I did a lot of VO2 max on soldiers. So these are the typical VO2 maxes of young active people. 3-4 times a week, you're not competitive, you're just active, you run regularly. This is likely to be the VO2 max. Right? If you're sedentary, okay, if you're sedentary, this is likely to be the VO2 max, about 25 to 40 mils per kilogram of body weight per minute. If you're heart patient, all right, or if you're morbidly obese, this is the kind of VO2 max you're looking at. And notice here, there's an overlap between obesity, heart patients, and sedentary individuals, right? This can go up to 32 or so, and this can be as low as 20-something that falls somewhere here, all right? So this gives you a sense of when you measure VO2 max, how to categorize the individual. The next thing I want to show you is how to use VO2 max then to convert that into calories. Now, the basic conversion factor you need to understand is for every liter of oxygen you utilize, you expend 5 calories. The exact number is 4.8, okay? 4.8 kilocalories or 5 calories. So we use that to estimate calories for the individual. So I'm just, okay, so this is a conversion factor. Every liter of oxygen uptake is 4.8 calories. So this is just an example, 20-year-old, 70 kilogram male. When he sleep, right, at rest, this is the amount. He's using 3.5 meals per kilogram per minute. So you multiply this by 70 kilogram, right? You get, and you multiply this by 70 kilogram, you multiply by this, you get about 14.7 liters of oxygen utilized when he sleeps. This is accumulated over the sleeping time, okay? Sorry, for every hour. So you just need to multiply 3.5 by 70 kilogram, and you get so many liters of oxygen. So when he works, this is the energy expended. Let's say he does a bit of physical work here and there. He uses about 12 meals of oxygen per kilogram per minute. You multiply 12 meals by 70 kilogram, you get 50.44 liters per hour. This is times 60 minutes. Sorry, you got to multiply by, so multiply by body weight, multiply by 60 minutes to get 1 hour. So liters per hour. So every hour is using so much of oxygen for doing sleeping and work. Recreation, he goes home, he play a bit of badminton with the family or so, or you go for brisk walking. This is the estimated energy expenditure. You multiply by body weight, you multiply by 60 minutes. This is the amount per hour. So every hour, this will be the energy cost in terms of oxygen. So assuming he sleeps and he rests, so sleeping and resting about 15 hours a day, right? That's not too different from today's lifestyle. So 15 hours times 14.7 liters times 4.8 calories per hour per liter, you get 1,058 calories just by sleeping and resting. When he's doing active work, right, 50.44, say he does active work for 4 hours in a day, multiply by 50.44, multiply by 4.8, this is the energy expenditure in calories. Recreation, this is the amount. So let's say he does 1 hour recreation, multiply by 147, multiply by 4.8, this is the caloric intake. You add this up, this is the energy expenditure for the entire day. So you can use this. If you have someone you're doing measurements on, you can use the same approach. If you are able to measure their VO2 doing the different tasks, okay? If you do not have the opportunity to measure VO2, you can go to the internet. There's this compendium called Compendium of Physical Activities. It's well validated. And within that, there are hundreds of daily activities that people do, from gardening to cooking to mopping the floor. And they give you the energy expenditure, like what I just explained to you over here. You can use that to estimate energy expenditure for yourself or for people that you're working with. Another way of expressing VO2max is metabolic equivalent, right? If you read the literature, if you read some research papers, they don't use VO2, they use MET. I just want you to understand 1 MET is equals to 3.5 meals per kilogram of body weight per minute. And 1 MET is equals to resting metabolic rate. It's an estimated resting metabolic rate. So when we say that your energy expenditure is 3 MET, we are saying that your energy expenditure is 3 times the resting energy, your resting metabolic rate. And this is how MET is being used. Okay, so in sports science, when you do exercise prescription, they'll say light intensity exercise is below 6 MET, for example, below 4 MET. High intensity exercise is above 9 MET, for example. So this is what they mean. 9 MET means 9 times 3.5 meals per kg per minute of VO2, and that's the amount of energy expenditure. 9 MET means 9 times of resting energy expenditure. Okay, so this is just a way of calculating energy expenditure. I just want to show you some research data on VO2max. How much can you train? How much is related to genes? And this is a study that was done on 112 families, intact families in America. And they trained the families for 20 weeks in endurance training, right? And look, the average improvement in VO2max was 18%, but the range was from 0 to 53%, meaning that over the 20 weeks, there are people who don't improve at all. But there were people who improve as much as 50% in VO2max. Okay, and they find that the main finding is that your improvement in VO2max was not influenced by your age, your sex, or your race. The improvement, how well you improve in VO2max was determined mainly by the genes. So that's why genes play an important part. And because of that, when you train one group of people, you cannot expect everyone to improve in the same way, because you got to make room for slow responders, low responders, meaning that you can train very hard, but they improve very little. You need to make room for slow responders, meaning that they may improve as much, but they will take longer time to improve. Okay, all right, and yeah, low responders, and then late responders as well. Okay, so genes has a big role to play in how much improvement one can expect in VO2max. Yeah, now that we have COVID-19 and there's an issue about wearing masks, and I was asked some time ago, what's the effect of wearing masks on exercise? And I gave a talk on this a while ago, and I just want to explain to you the impact of the role of respiration, the role of ventilation in oxygen delivery. Okay, so just a quick revision of respiratory physiology. We breathe in air, and this is at sea level. This is the gas content of oxygen, 20.93, 0.3%, and 78.6%. Okay, so for every liter of air, you get about 21% of oxygen, 3% of CO2, and the rest are nitrogen. So we breathe in from ambient air, it goes into our airway, it goes into our lungs, right? From our lungs, you get our venous blood coming to our lungs. The blood will then download CO2 to the lungs. The blood will then pick up O2, right, oxygen from the lungs, and that blood transported to the blood. Heart will then pump the blood to the tissue, isn't it? The tissue will then extract oxygen and produce CO2, and that CO2 and whatever remaining oxygen will then come back to through the venous blood, and then the CO2 is downloaded here, and that CO2 and the leftover oxygen will be expired to the ambient air. So just a very quick revision of respiratory physiology. I want you to remember, when you look at the lungs and VO2, there are three things you need to bear in mind. The first is the movement of gases, or the movement of oxygen and CO2 is driven by a gradient. Gradient means there's a difference in concentration, okay? Right, never mind all the words here, just remember gas pressure gradient. Remember, don't worry about the rest of the thing. And I want you to see here, right? This is the gas pressure of oxygen in the air. It's 159 millimeters mercury. By the time it goes into the airway, it loses 10 millimeters mercury to 49. So because there's a difference in pressure, air will flow in this way. By the time it gets into the lungs, we are left with about 100 millimeters mercury. Because the pressure is low here and high here, air will move from here down to the lungs. Look at the pressure of oxygen in the venous blood. In the blood that's coming to the lungs, it's only got 40 millimeters mercury. There's a difference of 60 millimeters mercury. Because of that, the oxygen in the lungs will move into the bloodstream. Okay, so the pressure the pressure difference will drive the direction of the gas. So when the oxygen get delivered by arterial blood to the tissue, in the arterial blood is 100 because it picked up 100 mmHg here. In the tissue, it's only 40 mmHg, 40 millimeters mercury in terms of pressure. And because of that, oxygen is downloaded in this way because of this difference in pressure. On the other hand, you look at CO2, right? When in arterial blood, it's only 40, but more CO2 is produced in the tissue. And because of that, the gas is then being pushed out into the venous blood. And look at here, in the lungs, CO2 is 40 millimeters mercury, in the blood is 46. So the gas will move this way. So gases move by pressure differences in the blood. Okay, and this is how we get oxygen moving one direction, CO2 moving in the other direction. The other thing I want you to recognize is the importance of hemoglobin. And this is where there's a difference between male and female, right? So for males, for every 100 ml of blood, we carry 15 grams of hemoglobin. For females, you carry about 13 grams of hemoglobin per 100 ml of blood. For each gram of hemoglobin, we carry 1.34 ml of oxygen. So you multiply 15 grams by 1.34. For every 100 ml of blood, males, we get 20 ml of oxygen. For females, we get 17.4 ml of oxygen. I hope everyone is okay with this. Yep. Okay, so males, for every 100 milliliters of blood, you get 15 grams of hemoglobin. For each gram, you get 1.34 ml. You carry 1.34 ml of oxygen. You multiply that, for every 100 milliliters of blood, you get 20 ml of oxygen. For females, you do the same, but with 13 grams, you get 17.4 ml of oxygen. Now, in intense exercise, our body push about the cardiac output, right, is about 25 liters. So every minute, your blood is pumping out 25 liters of blood, supplying your muscle with 25 liters of blood. You divide the 25 liters by how many units of 100 ml of blood. Okay, so at 25 liters is about 250 units of this. So 250 ml of blood multiplied by 20 ml. For 25 liters, you get oxygen supply of 5 liters every minute to the muscle. For females, for the same amount of blood your heart push out, you do the same, you get 4.3 liters of oxygen delivered to your muscle. So this is why, as I explained to you earlier, one of the reasons why females are disadvantaged over males in terms of VO2, in terms of endurance sports, is because of the difference in the amount. One of the reasons is because of the difference in the amount of hemoglobin in the blood. The next thing I want you to bear in mind is now you go altitude training, right? So one of the effects of altitude training is an increase in the hemoglobin, amount of hemoglobin in the blood. So assuming you go altitude training, and because of the increase in hemoglobin, you can increase the amount of oxygen you carry just by 3 ml. For every 100 ml, you increase just by 3 ml, 3% increase. Look at the difference in VO2 per liter. For every minute, you can deliver another almost close to a liter of oxygen to the muscle. And this is how effective changes in hemoglobin can be in delivering more VO2. The last point I want to highlight to you is that, as we said earlier, VO2 is a function of how much gas you can deliver multiplied by the volume of air you can deliver. When you wear masks, right, and if the mask obstructs the air exchange, then your VO2 will also be affected. Okay, as I said, this was the formula I showed you earlier. Force inspired, the volume, the oxygen multiplied by volume of air intake. If this volume is reduced, that means your VO2 will also be reduced. Now, I want to show you a study that I did many years ago with my colleagues in the hospital. Before COVID happened, the concern with N95 masks is not during sports. The concern with wearing N95 masks was in pregnant women, because if you're pregnant and if the mask reduces oxygen intake, the question is whether will it affect the fetus. And so we did a study on pregnant women, 20 of them. They were at the last trimester of pregnancy, about 27, 32 weeks of gestation. And we walked them on the treadmill for 30 minutes. The 15 minutes was without the N95 mask, and another 15 minutes was with the N95 mask. So this is it, without the N95 mask, another 15 minutes, the mouthpiece had an N95 mask over it, all right? And this is what we found. This is walking very slow. 3 mat is slower than normal walking speed because they're pregnant, so we've got to be very careful with them. Tidal volume, the volume of air intake per breath. Now, the light dot is the control that means without N95, the black dot is with N95. Okay, at rest, just at rest alone, there's a reduction in the volume of air that you breathe in every breath. During light intensity work, the volume of air dropped by 23%. Okay, but during recovery, there's compensation, and we were able to, the body was able to compensate for that. So just wearing the N95 mask alone, you get almost 1/4 reduction in air volume intake. Okay, now breathing frequency doesn't change because the workload is very low, so there wasn't a need to breathe harder to compensate for the drop in air volume. Minute ventilation is the volume of air you expire every minute. Okay, so again, the black dot is with N95, the white dot is without N95. So at rest, there's a slight difference. When you come to exercise, during 3-MET, you see a drop of 26% in air exchange, okay? FeO2, this is the forced expired O2, how much oxygen you're expiring for every breath. Again, you see a reduction in oxygen expired, okay, when you're working, and this is the amount of carbon dioxide that you expire. You see an increase, so you get a reduction of 9% in expired O2. You breathe out 3% more carbon dioxide, and VO2 dropped by about 14%. So this is the impact of wearing N95 mask on a ventilation. So there is no study done on athletes wearing N95 mask or any kind of surgical mask, but the implication now is that if you're doing light intensity work, you should be able to cope with wearing masks. But once you're doing intense work, intense physical exercise, the mask will become a barrier to your exercise performance. Okay, I think in the interest of time, I will skip this. Yeah, and I want to talk to you about this slide. No. Okay, so maybe we'll skip this. Okay, I want to share with you about this slide, and this is important because of the aging society that we live in. So this is a study that involved 102 persons. They're all more than 64 years old. And these people are healthy. And the researchers have been working with them for more than 25 years. They know their exercise history. There were 27 of them who were sedentary, who don't exercise at all, less than once a week. 25 of them were casual exercisers. They exercised 2 to 3 times a week. 25 of them were committed. They exercised about 4 to 5 times a week. Another 25 were competitive. They train 6 to 7 times a week and they compete. Okay, and they did, they measured different cardiac function in these people. The first thing they measured in them was VO2max, right? This is what everyone does in exercise science. So you can see that as the level of the volume of exercise increases, the VO2max also increases. And it comes back to my point that with training stimulus, you can maintain your VO2max much better. So this was the average. If you're competitive, about 40 something, those who are high can go to close to about 50 mils per kg per minute. Okay. This is stroke volume. Now, stroke volume is important, right? As you know, this is the amount of blood your heart can pump out every minute. It's half of what accounts for cardiac output. Okay. And same thing, the harder you train, this is sedentary. Okay, so for each time, this represents the amount of time the heart pumps. Each time the heart pumps, the people who are sedentary will have the lowest stroke volume, followed by casual, competitive, and committed, and those who are competitive will have the highest stroke volume. And that's the benefit of training to your heart. And stroke volume is part of cardiac output. Cardiac output is part of VO2max, right? This slide here, on this side, it refers to the pressure when the heart pumps. On this side, what you're looking at is left ventricular end diastolic volume. This is the amount of blood that fills the heart, the left side of the heart when the heart expands. And this is important to understand in exercise physiology. Is it the expansion of the heart that helps you to have a high VO2max? or is it the contraction of the heart that allows you to have a high VO2 max? And we look at this data, right? For the same contraction force, this is sedentary, this is casual, this is committed, this is competitive. That means the higher trained you are, the higher VO2 max you have, the more your heart can expand in the heartbeat. The more your heart can expand, the more blood can fill the left ventricle. And because more blood can fill the left ventricle, you can push up more stroke volume, you can push up more cardiac output. And because of that, you can have a higher VO2 max. This is one implication. The second important implication is this. Now, one of the things that happens to our heart when we get older is that the heart loses compliance. In other words, it becomes very stiff. It cannot expand. Okay? And when your heart cannot expand, at the very worst case, it becomes very stiff. You go into what is called heart failure. The reason your heart fails is because the left ventricle is very stiff. The muscles cannot stretch. And what it shows you here is that people who are fit, right? The more you go up to this side, the more the heart can stretch, open up to receive more blood. The stretchability of the heart muscles are maintained over a lifetime. And VO2 max is a very good indication of that, because VO2 max requires the heart to stretch so that it can pump, it can contract forcefully and pump out more blood to have a higher stroke volume. All right. So this is a very nice study done. It was very invasive. They actually put a catheter up the heart to measure these things. But it's a very nice set of data that I hope that you learn to appreciate as well. Okay, I think I will just stop here. So we've covered a lot today. We've covered the history of VO2. We've covered the physiology of VO2, the measurement of VO2, the application of VO2, and also look at how VO2 can help us in our aging health as well. All right, perhaps we can go for question. Yeah, if there are questions for me.
Okay. Prof Fabian?
Yeah.
Okay, do you want to continue your presentation or question time?
Are there questions? If not, then I can stop here. I just have 2 more slides.
Okay. So if any question, please raise your hand, or you can ask him directly to Professor Fabian Lim. Actually, this is very wonderful presentation about how we get VO2 max and how to calculate it, right? And I think the students now have so many tasks because they will calculate themselves how much their VO2 max themselves, and then they will calculate about
energy expenditure.
Energy expenditure, yeah.
It's a very good lab session, actually. I do that for my students as well. Yeah.
So after this lecture, they will do that task. Please,
okay.
Please, you can ask your question. Silakan untuk bisa menanyakan pertanyaan kepada Profesor Fabian Lim. So this is one question. If we want to increase the VO2 max for the athlete in the competition time, this is have a correlation when when before competition they give oxygen spray or oxygen can, or they drink oxygenation drink. Is it have a correlated to VO2 max?
Yeah, the short answer is no.
Yeah.
And the reason is that if you go back to, that's why understanding the fundamentals is very important. If you go back to what I shared with you about the Fick equation, cardiac output and AVO2 difference, right? Oxygen
Yes.
delivery and oxygen utilization. Having more oxygen in the blood, assuming it does, doesn't necessarily means that you can extract more, okay? So training the muscle to extract is the only way that I know that allows it to extract more oxygen. Delivering more oxygen through higher cardiac output by having more red blood cells, yes. The other thing I want to explain to you is this. Now, the amount of oxygen in the blood is very tightly regulated. How much oxygen you can have in the blood is tightly regulated. So I calculated for you, right? For every 100 mils of blood you have so much of hemoglobin, and you can only carry so much of oxygen. And those are tightly regulated. So even if you swallow water that has got oxygen in it, even you breathe in high oxygen content air, it doesn't mean that your blood will carry more oxygen. And in fact, you've got to be careful because oxygen by itself can be poisonous if it's not carried in the blood. Yeah.
So too much oxygen can be poison.
Correct.
And then actually so many questions. So how your suggestion for sedentary people, because they only 1 week to do exercise, and how to increase their VO2max? There must be exercise, right? And how must they do for only 1 week to increase their VO2max?
So I think for sedentary people, the first consideration is not VO2max first. The first VO2max, as you pointed out correctly, Tintin, is to increase the physical activity level, right? I think that's the first thing. So I always say that if you're helping someone sedentary, the first 6 months is behavioral modification. You're not concerned with whether they are walking so fast, they're running, they're running so many kilometers. You're not concerned with that. You're more concerned about how many times a week can they change their lifestyle to participate in physical activity. The good thing now is that the international community has recognized that you don't have to do 3 times a week, 60% VO2 max, 60% of maximum heart rate to benefit from health, to benefit from exercise. The public health message is 150 minutes every week. So 30 minutes a day, and you don't have to do 30 minutes at one go. You can accumulate 5 minutes, later on another 5 minutes, later on another 5 minutes. And it need not be exercise. It can be housework, it can be gardening, it can be, going from place to place. The main thing is to reduce the sitting time and increase the movement time. So starting with that, and then moving on to more structured exercise program, once a week, twice a week, and so on. Yeah, would be the way to go for the first 6 to 9 months. Once they have improved, they are regular in their exercise program, they have changed the behavior, then the next step is to look at changes in their physiology and the rest of the things. Okay?
Okay, thank you. And this is one question from Dr. Anis. So how long when before you have a research about N95, right? And how long when they put N95 and this is have a correlation with VO2max, the result?
So we didn't measure VO2max because they were pregnant, but we did measure VO2.
VO2. Yeah, I'm sorry, VO2. Yeah.
15 minutes. So 15 minutes with the N95, 15 minutes without the N95 mask. So they walk on the treadmill and we just change the mask at 15 minutes.
So change the mask every 15 minutes.
Yeah, 15 minutes. So half the subjects start with N95 first, another half start with no N95. And 15 minutes they change over. So they walk on treadmill for half an hour. Half of it is with N95, half is without.
And then?
Yeah, so that's how we measured.
Okay.
Yeah, we couldn't go too long because if there's hypoxia, we didn't want to, because they're pregnant, we've got to be very careful.
Yes, because pregnant, right?
Yeah.
And then, okay, the students, anyone asking again, this is very interactive actually. Very excellent presentation and make we ask clearly how to understand the concept of physiology. Okay. Okay, maybe you can the next presentation or finish.
Yeah, I think
The slide.
I would
Still have to slide or finish, right?
Yeah, it's just for predicting VO2max. Or maybe I'll just spend 5 minutes finishing it. Okay, so I just want to share with you. It's quite well established now. You can use VO2 and then lactate measurement and running economy to predict endurance performance. Okay, I won't go into any of this, but I just want you to know that the VO2 that you can run at, your VO2max, your lactate threshold, and your running economy. That means how effective is your running technique. These three factors are the most important in determining endurance performance. So there was a study done where they compared what I just showed you, the three things, the three factors to predict endurance performance. Okay, and another one is just by looking at peak treadmill velocity. In other words, from Tim Noakes suggested that if you just look at what's your fastest speed you can maintain it on the treadmill, you can predict your endurance performance. Okay, so this was a study that was done to look at different ways of predicting endurance performance with VO2max as one of the measurements. All right, so comparing peak treadmill velocity with what we just talked about. So 17 of them and trained endurance athletes, they did five different runs on 5 different days, and this is the result that we got. Okay, so how do you measure something and predict the actual performance, right? So if you use what I just explained to you, your VO2max, lactate threshold, and running economy, you can predict 95% of endurance performance. If you use peak treadmill velocity alone, how fast you can run, the fastest speed on the treadmill, you can predict about 80% of endurance performance. Okay, now if you combine these two prediction, you put them together, you can predict about 98% of endurance performance, close to 100%. That's very useful. Just VO2max alone, if you don't do anything else, you just measure VO2max alone, you can predict about 90% of endurance performance. Now we're talking about running or cycling. Yep. Just pure one single activity, not a mix of running or cycling. Okay. And if you put VO2max and running economy, just running economy and VO2max, you can get 97% accuracy in prediction. So I just want to highlight the last slide here, okay, that just having VO2max measurement alone, or just with VO2max measurement and running economy, you can actually have quite a good chance of predicting endurance performance. So you have a group of runners with you. You want to know who is likely to perform better, let's say in a 10K run, in 12K run. These are the different methods that you can go through to do that. All right, so that's my last slide. Okay.
Okay, thank you very much, Professor Fabian Lim. Very excellent presentation and really very clear for us. And
I hope it's not too confusing for you all. Yeah.
And this is have one question again. Is it okay from Dr. Yeti Makarina?
Yes.
Okay. As how long for weeks or months exactly someone have to do exercise to improve VO2max, especially for untrained person?
Okay, so if you're untrained, right, you can see changes in VO2 and VO2max in about 6 to 8 weeks. That's if you're assuming that you're doing, for example, brisk walking, about 3 to 5 times a week, just brisk walking. You can see changes in VO2 peak, I would say, VO2 peak in about 6 to 8 weeks. So one of my very first research I did was on obese soldiers. I don't know, you all know, Singapore run the biggest weight loss center because, all our young men has to go into the army. And every year we have 12% of childhood obesity. So we have 12%, about 1,000 to 2,000 of them were obese in the military.
Wow.
Yeah. So in the 1990s, we started a special program for them, and I actually published 2 papers measuring their VO2max and so on. They lost a lot of weight. They lost about 15, 20 kilogram of fat, mostly fat, and VO2max improved during that time. But this is military training. But in civilian, you can see changes, assuming that they do brisk walking every, do brisk walking 3 to 5 times a week, especially they can go 5 times a week. And you can see quite good changes in about 6 to 8 weeks. Yeah.
Okay, 6 weeks.
Yeah.
Thank you, Professor Fabian Lim. And one more.
Okay.
Is how to predict, what do you think about prediction of VO2max using PIP test running?
Yeah.
Is it okay?
So there's still quite a lot of error because the PIP test running was developed using young healthy people. Right? So if you use that on a different population, firstly, the response will be different. The heart rate and performance and VO2 relationship will be different. Okay, so those are useful as a benchmark. So for example, you do a me today, and then you train me. 6 weeks later, you do my BIP test again, then you predict a VO2max, and 6 weeks later, another 6 weeks, you train me again. So within myself, I can see that my BIP test result has improved. My VO2max has improved based on the BIP test result. It's useful for that purpose, having a consistent measurement. But whether is it accurate is a separate question.
Yes.
VO2max number is truly that number is a separate question. I was just having a discussion about this a few weeks ago. I conducted a workshop. Same thing, the watches that you have, nowadays you have a lot of wearables, they predict VO2max when you run, the watches, all those there are a lot of errors in it. But if you use it as a benchmark for yourself to see, have you improved from stage 1 to stage 2 to stage 3, it has that purpose. Yeah. I would use heart rate as a more accurate measurement.
Okay, heart rate, maximum heart rate.
Percentage of maximum.
Percentage.
Yeah. And exercise heart rate. So if your fitness has improved, right?
Yes, right.
The same amount of work, your heart rate should come down, isn't it? Yeah.
Thank you.
Okay.
Thank you, Professor Fabian Lim. And for participants, so you have so many knowledge now, and you have tasks you for message to home, take home message. So all of you can try to calculate first from your energy expenditure and then how much your hemoglobin. And this is so many, I think. So maybe after this, I can make a note for you in the WhatsApp. So thank you, Professor Fabian Lim. Maybe for the last, we can take a picture together. Please,
okay.
Please on your video all.
Let me see, how do I do that?
Yeah.
Let me do that.
Okay. Silakan untuk di-on-kan videonya. Mas Muhammad Fauzi mungkin bisa bangun. Oke. Silakan bisa di-on-kan dulu videonya untuk diambil fotonya. Yang sedang tidur bisa kelihatan. Today, so many participants have 210 before, 210 participants. So not only for undergraduate student of sports science, also magister of sports science, also from the other university join
Oh, I see.
with
Okay.
this. And the Association of Physiology in Indonesia also join in here.
Oh, thank you. Thank you. Yeah.
Yeah.
It's my pleasure to be sharing the information with you.
And please take a picture. Pak Mustafa mungkin bisa membantu. Terima kasih. Oke, silakan Ade, Kalneva, Imam, bagus. Silakan bisa di-on-kan videonya. Arsan. Oke. Slide 1. Slide 2. Oh. In here also still have Professor Dr. Setio Rahayu, Professor Fabian Lim, and still have the Chief Department of Sports Science.
Yeah, thank you very much.
Thank you. Thank you.
Prof Fabian Lim.
Thank you.
Next week, yeah, in Magister program for sport education.
That's right. Thank you. It's my pleasure to be sharing with so many of you. Yeah. I hope we can have more exchange between our universities.
Yeah. And then third. Okay, third. Okay, Dr. Yeti, thank you from Medan. Dr. Anis also have here. But Suyatno, Mr. Suyatno also have in here. Welcome. And then number 4, Via Fitriani, where are you? Okay, Dita Afton Nurdin. Oke, silahkan. Why the last is no one on the video? Where are they? They're sleeping or where are they? Oke, silakan ditampakkan wajahnya satu persatu. Dan jangan lupa untuk mengisi link sertifikatnya. Dan ada PR untuk dibawa pulang. Silakan diukur bagaimana cara menghitung energi expenditure, kalorimeternya, dan berapa jumlah hemoglobin di dalam tubuh kita. Oke. Okay, the last is no, 7. Still have 7. 7. Okay. Professor Fabian Lim, see you next week. So next week we'll have exercise physiology again about lactate threshold.
That's right, yeah.
Yeah.
Okay.
So it's very important in exercise physiology how the lactate threshold happen.
That's right. Yeah.
So please join with us again and with Professor Fabian Lim on Tuesday at 5 p.m.
Thank you. Thank you, everyone. Thank you very much.
Yeah.
Thank you.
Thank you.
Bye-bye.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Bye. Okay.
Bye.
Kioknya bagus.